Hello everyone. In our previous video we have seen the definition of simple harmonic motion, right? So now here we will see explanation of simple harmonic motion clearly. Explanation of simple harmonic motion, and that too I will be taking like the help of a reference circle. We'll be taking a reference of usage of reference circle. So sometimes this reference circle topic can also be stated as like projection. Okay, projection of a particle, projection of a particle moving in uniform circular motion, moving in uniform circular motion, uniform circular motion about any diameter, about any diameter is SHM. So they can even say this as also like explanation of SHM by reference circle. So if you had such a kind of question as this, you can take the help of this explanation what I would like to explain in this particular video. So for this I am just considering a circle. So straight away I would like to draw a circle over here. So this is the circle, and say that the center of the circle being considered over here and denoted as O, you can say like, and before you can say like there are two diameters. So this is your, let me say, diameter 1, that is along x axis you can say, and this is another diameter along a y axis, and thus this is your center O. This is your center O, and I would like to take this diameter as x and x dash, and say this diameter, vertical diameter, as y dash, and considering a particle P. So I would like to consider a particle P over here, and this particle P is now moving in this uniform circular motion, and in this uniform circular motion I would like to take this as particle P over here, and then the particle P is moving in this circular path. The particle P is moving in this circular path and considered uniformly, and that too it is said to be moving with an angular velocity omega. It is said to be moving with angular velocity omega, and I have taken in anti-clockwise direction. So if I would like to join this particle P from the center, so this is your like what you call this diameter you can say, and sorry for this, and it is like this, and say the particle P now has covered an angular displacement theta, and the time taken from, let me say, from this position to this position, an angle theta, that is your angular displacement covered, and say the time taken be some t. So with angular velocity omega, in a time t, the particle P covered a displacement of theta. So therefore now I can express theta as omega t. Already we are very much familiar with this. And now, as I said, the question can be asked like this: projection of particle P about any diameter. So now I would like to take this projection with different colors. So projection of P along y-axis, I am just showing it with a red one. And what is the projection? That is nothing but your straight away perpendicular drawn from the point P onto the y dash, that is your vertical diameter. Clear? And now I would like to show the projection of the particle P about the diameter x dash with blue dotted line, and this is your projection, and say this is again perpendicular drawn simply as usual. So now you can say this is the displacement of the particle about this diameter, say this is y, from the origin, like mean position O, and say this is your displacement of the particle about x diameter. Say this is your x, for all the things I've just considered in this way. Clear? I hope everyone have understood this one in detail. And now let us go into this understanding this particular thing, and say this radius of this circle, whatever reference circle I have taken, be A. Say the reference circle radius be A, and as this is theta here at angle at center O, now this angle at P also can be considered as theta. P also can be considered as theta. So therefore already we know that theta is equals to omega t, and from this we can just simply write down this one. We got it because angular displacement definition is what? Change in angular displacement by change in time taken by the particle. So from this we have got theta is equals to omega t straight away. So therefore in the triangle, so let me say this particle be some d, this position. So from triangle O, D and P, we are having theta. So now we are going to take the relation between y and a simply. So let me say this one, you can say sine theta. So sine theta is your opposite side by hypotenuse. In that the right angle triangle, opposite side is your y and hypotenuse is your a, that is a radius. So therefore we are going to get it as y is equals to a sine theta, and this displacement I considered along diameter y dash, along diameter y dash. So we would like to write this one along x-axis also in the next part after this one. So y is equal to a sine theta. Since theta is equals to omega t, let me substitute here. So y is equals to a sine omega t. So what do you mean by this y is equal to a sine omega t? Means here whatever the particle, the projection of the particle moving along y dash is varying such a way that y takes the equation or expression as a sine omega t. Now I have to prove this particle or the projection of this particle about this diameter is a SHM. That is nothing but your simple harmonic motion. So what is simple harmonic motion? Already we have seen that acceleration of the particle should be directly proportional to its displacement, that too in negative, opposite in direction. So if I can show this one clearly for this taken expression y equal to a sine omega t, then I can say that the projection of this particle is clearly executing simple harmonic motion. So for that what I can do clearly? So y is equal to a sine omega t. So differentiate, and I would like to take this one as equation 1. Differentiate equation 1 with respect to time t, So therefore I get d by dt. So differentiation with respect to time t of displacement is equals to a is anyway constant, comes outside, a into d by dt of sine omega t. So the rate of change, that is nothing but differentiate of displacement gives you velocity. Already we know that. So therefore velocity v is equals to a into differentiation of sine theta is your cos theta. So that is cos omega t into, and this applying the chain rule here, so d by dt of omega t. So thus you get v is equal to a d by dt of omega t is omega a omega cos omega t. Done. So we have got velocity expression. So v is equal to a cos a omega cos omega t. Say this is be equation number 2. So again differentiate this with respect to time t. So differentiate equation 2 with respect to time t again. So we will get it as like d by dt of velocity v on left hand side and a omega anyway constant into d by dt of cos omega t on right side. So thus differentiation of velocity gives you acceleration a, that is a omega into d by dt, that is differentiation of cos gives you minus sin theta. So therefore minus sin omega t. As usual, again chain rule. So d by dt of omega t. So therefore you get a is equals to minus a omega into d by dt of omega t is again omega sin omega t, sin omega t. So thus acceleration a is equal to minus a omega square sin omega t. So I would like to write this one as like this. Acceleration a is equal to minus omega square into a sin omega t. So we have seen this a sin omega t somewhere, right? So what is this a sin omega t? From equation 1, that is y only. So from equation 1, this can be rewritten as a is equals to minus omega square y. So let omega square is equals to some constant k. So therefore we get a is equals to minus ky, and I can write a is proportional to minus y. So this proves that the particle executes simple harmonic motion. So this is your explanation of simple harmonic motion using a reference circle. So now you can get a doubt. Sir, you have explained along y-axis. So why don't you explain us along a x-axis now? So take the same triangle. So I would like to take this triangle now. So this is D, right? So I would like to take this one C here. So take triangle OCP. So now from triangle OCP, we require the relation between this x and a, so we take cos theta. So therefore cos theta is equal to x by a, from which I will get x is equal to a cos theta, and already we know theta is omega into t. So therefore I get x is equal to a cos omega t. X is equals to a cos omega t, where x is nothing but displacement along diameter xx dash. In the previous case, y is displacement along diameter y dash. So x is equal to a cos omega t. Say this is equation 1. So differentiate 1 with respect to time t. As usual we will get like, so dx by dt is equals to a into d by dt of cos omega t. So already previously we have done this. So let us do it in detail now. V is equals to minus a omega sin omega t, because differentiation of cos is minus sin and differentiation of omega t is omega. So straight away I have written in one single step. Say this is equation number 2. So now again differentiate 2 with respect to time t once again. So we will get like dv by dt is equals to minus a omega into d by dt of sin omega t. So this proves that this is acceleration a, and this is as usual minus a omega square cos omega t, and you know that differentiation of sin takes cos and differentiation of omega t is omega. So therefore again a is equal to minus omega square into a cos omega t. So from equation 1 you can say acceleration a is equal to minus omega square x. So let omega square be some constant k. So therefore a is equals to minus kx, and again acceleration is directly proportional to the displacement taken in opposite direction. So thus again along xx dash also the particle is possessing or executing simple harmonic motion. So thus it is proved that the projection of a particle moving in a circular motion executes simple harmonic motion about any diameter. So hope you everyone got understood it. Thank you very much. Have a great day. Any doubts, please post in comment section.